Sure. Okay. So thanks everyone for coming. So I guess the purpose of this meeting is for me to just describe just generally what Edward is all about, and hopefully I can orient this to however it most benefits you all. And I'm very invested in helping make Edward a thing for Dyna and HEP in general. So I'll be presenting Edward's Library for Probabilistic Programming, and it's this library that we've been developing for almost a year and a half now. It's mostly been work jointly from our group in Columbia and also a lot of friends from Google Brain. To give some just some motivation, I'd like to start with some applications. So in this first application, what we're interested in is just analyzing a bunch of articles from the New York Times. There were 1.8 million articles, and a typical task we do is just exploratory sort of data analysis. So in this particular application, what we're doing is positing some generative process for how the articles arise, and this generative model posits this hidden structure known as topics. And if you perform some form of inference on this model, in other words, calculate distributions over the hidden structure given some data set, you can uncover interesting phenomena. So in this example I'm showing just a bunch of topics, which are global information that's shared across all these documents. In another application, what we're interested in is analyzing a bunch of genetic measurements. In this case, what you might imagine is that the data comes in this very large matrix. Each of these columns represents a particular individual, and each of these rows represents a causal genetic factor. In other words, people have gone around and sequenced a bunch of individuals, and what they essentially sequence is millions and millions of these zeros, ones, or twos, which are your nucleotides. And what we're interested in here is trying to understand ancestral populations. In other words, given that you're a person, what sort of ancestries have mixed in order to form genetic factors. And through something that's very similar to a topic model, you can uncover this interesting phenomena where each of these colors represents an ancestral population, and through inference, through inferring these ancestral populations, you can uncover that many people are an admixture of many different populations. For example, there's some heterogeneous people which are just typically orange, or there's homogeneous people which are typically orange, and there are also heterogeneous people which are a mix of other colors. In this example, this is more of an artificial intelligence example. Here we're interested in scene understanding, concepts, and control. I'll just go through these applications slightly faster. In another application, we're also just interested in analyzing scientific data sets. So this one, we're doing exploratory analysis of taxi trajectories, posit a dynamic sort of mixture model, and we can cover interesting phenomena in this city of Porto. And finally, in this last application, we're interested in image compression, content generation, where we're just getting a bunch of videos or images, and we're trying to understand or even generate new images. Okay, and so we showed a bunch of these applications, and we'd like to understand like what commonalities sort of existed. Well, in all these applications, what we've really done is we posited some generative model, some process for how the data actually arised, and we formed some form of inference. All the inferences may not be different, but it's just a way of training the parameters of the model given your data set. And if we'd like to build some library to allow all this sort of experimentation, we'd like to understand sort of the fundamentals for how this process arised. So here I'm going to take a step back a little bit and show this figure, George Box. And he is in particular a preeminent sort of statistician from the 20th century, and we're going to look at one thing that he posited. And this is going to be some iterative process for science, and it goes as follows. The first step is that you're first going to build a model of the science. So given some scientific phenomena, you're going to posit a theory for how that science actually came to be. Second, given like some experiment where you have experimental data, you're going to make inferences on the model's hidden structure given your data set. In other words, given your current set of theories and given your experimental data, how do you aggregate these things to make or update your new theories. And third, and perhaps most importantly, given that you've just updated your theories, you want to criticize how well your current model fits that experimental data. And as you do the criticism, you better understand your strengths and weaknesses of the model, and this gives you the better revise the model, going back to step one, where you rebuild the model. And if you go through this process, you are essentially forming this loop. And so more succinctly, all you're doing is you're building some model, you're performing inference, in other words, you're fitting that model conditional on some data set, and then you're performing some form of inference, or some form of criticism of that model, of that fitted model given your data set. And we call this loop boxes loop, and Edward is a software library that's really designed around this loop. We're going to build a set of tools that allow you to build very flexible models. We're going to have the suite of infrastructure to allow you to do many different forms of inference. And we're going to have a bunch of evaluation tools that allow you to understand your model's fit. This idea has been around in the literature, and really what we're trying to do is just make this actually implementable. So we can take the ideas in principle and actually put them down in practice. Great. And here's a technical overview of what Edward is. So it's a probabilistic programming language. It's built around TensorFlow as the main infrastructure, and for each of these three things, here's what it does. So for modeling, it has a Turing-complete language for the random variables, and it has this large set of features to do very flexible modeling. You can support graphical models, neural networks, or probabilistic programs, and then for inference, you can have this composable sort of language that allows you to compose many different inferences together, and this allows you to do a bunch of hybrid techniques, which are very popular in the research literature. And examples of common inferences that have been applied in Edward are black box variational inference, Hamiltonian Monte Carlo, and more scalable versions with stochastic gradient descent combinations. And finally, for criticism, you have things like scoring rules, hypothesis tests, and posterior predictive checks.
Dustin, this is Kyle. Do you mind if I make a quick interjection here? So there's a lot of language barriers in these discussions. So I just wanted to double check. So in the modeling section, you have this first point that says composable language for random variables, and I think my understanding from Edward is that when you talk about random variables, you're thinking about, for instance, a random variable x might be distributed according to a Gaussian distribution for kicks, and so that Gaussian distribution is the thing that you're calling random variable there, right?
Yeah, that's right.
So in the RuFit language, we usually we often think of the random variables as sort of the specific values observed in data or in some simulated data set, and then we put a lot of emphasis on the probability density or the distribution or the PDF. And so, not that there's a problem, but just in terms of connecting between the language, I think that first part you're basically saying that is like the RuFit piece where we model the distributions, and then an inference side is a lot of what we would maybe refer to as kind of the RuStats language, which is what we stick those models into for doing our either Bayesian or frequentist type inference. And there, the list of techniques that you have, like black box variational inference, Hamiltonian Monte Carlo, and things like that, are not things that our field really uses very much at all. We usually have, essentially, we build some sort of approximate statistical, like we have a generative process, and then by hand we build a likelihood that models that data, and then we either do kind of straight likelihood type of inference, or we do MCMC in a Bayesian type of setting, but we're not very often doing these kinds of variational inference problems and things like that. So please add to that, but I just wanted to, since this is pretty key to the whole talk, I just wanted to try to help build bridges here to the physics community.
Yeah, I think that was very helpful. I won't go too much into details of how we do inference, but there are tools for both just likelihood-based ones as well as likelihood-free methods. And if we can somehow join efforts in getting Edward, we can definitely help on the likelihood-free part. I'll go over an example later that shows like a simulator-based model and how that might be used.
Great, and I think also this last part, criticism in the physics speak, we don't do a ton of that, and certainly not in that way of saying it, but usually we talk about some kind of goodness of fit test afterwards, right? You know, we have the best fit to the data, and then we basically want to see how well the model describes the data, and that's basically what you're getting at. But again, since a lot of these terms are not things that are common terms in the physics community, just
right.
Connect again. Yeah.
Yeah. You can think, yeah, that's exactly right. You can think of a predictive check just as a goodness of fit test. You're generating data from a model, and then you're comparing your generated data to the true data. And that test statistic is typically a goodness of fit statistic or other things. And also to mention for the backend infrastructure, there are many things that we're leveraging based on TensorFlow. And this allows you to scale these things up to leverage multiple GPUs. In our experience, we've been essentially applying this thing with 4 GPUs and parallelizing a lot of our computation, and it's really made a lot of our large-scale experiments very fast. Okay. And also just to give some overview of the community, so Edward has really blown up, and we've seen a lot of different applications and contributions from the community at large, which I think is very helpful. And maybe one way of understanding Edward is just through the user base. So I like to separate the user base into 3 sort of categories. One is sort of like your machine learning enthusiasts and data scientists, where they're basically just interested in like the fundamentals of probabilistic models, like hierarchical generalized linear models and maximum likelihood estimation. In the second one, you have the research community around probabilistic graphical models. And here they're interested in slightly more complex models and more approximate inferences, like latent Dirichlet allocation, which is a topic model, and various forms of Gibbs sampling and variational inference. Also, a more recent subcommunity that has sort of risen in the literature is one on combining Bayesian methods or just approximate inference methods with deep learning. And here you're combining neural networks with probabilistic methods to do the inference for you. And we also have many developers that have been helping on Edward. And if you're interested in collaborating, please contact me and also visit the forum. Okay, so maybe I can go through a concrete example of how to use Edward. So I hope you can all see this.
So just, I don't know what other people are saying. For me, I see it, but there's a delay between what I see and what you're broadcasting.
Okay, I can go slowly then. Is this large enough font?
Yeah, let's sit here.
Okay, so this is just a Jupyter notebook. You can go through the website edwardlib.org, getting started, and there's a link to it and all that stuff. So you can run and play with the code. So the first thing in the script is just a bunch of import statements, and here we are defining 2 different functions. So this first function is just building a toy data set. You can imagine this as a bunch of inputs which are linearly equally distributed, and then you just have a cosine relationship over the inputs. And then we add some normal noise. This is all written in NumPy. None of this is in relation to Edward just yet. We can ignore this function for now. And so first what we're going to do is we're going to build some toy data set of 50 observations, and there's only 1 dimension for the covariance. And we're going to put them into X train and Y train. And next, so given our data set, we're interested in positing some model, and here what we're going to do is define a 2-layer Bayesian neural network. What is a Bayesian neural network? Well, it's just a 2-layer neural network with prior distributions over the weights of the neural network. So what we're going to do is put down these 4 distributions. They're all standard normal distributions. So each of these has 0 location parameter and 1 scale parameter. So just 0 mean and 1 standard deviation. And we're doing some like intelligent broadcasting inside. So W0 here is actually a D by 2 matrix of normal random variables. Analogously, W1 is a 2 by 1 matrix of normal random variables. And B0 and B1 are bias terms that go into the neural network. This distribution is a conditional distribution, so we're going to write a distribution of y given x. X we're going to rewrite as x train, and for the outputs, what we're going to do is write a normal distribution. The mean of the normal distribution is going to be the output of the neural network, and we're going to fix the standard deviation to be 0.1. So let's go back to what the neural network looks like. The neural network is just a function. It takes in an input x, all of its weights and biases, and then it does matrix multiplication. So the first hidden layer is just doing matrix multiplication of x and the first weight plus a bias. It applies a tan H nonlinearity, and then it does matrix multiplication again. And so the output of this is just a vector of real values. And so I'm going to skip this and perhaps show you what a visualization of what this looks like. So I'm just writing down some matplotlib junk to plot the image. And so here's what the data looks like. It's just a cosine with some slight perturbations. And if you generate from the model, initializing the weights randomly, you get sort of these funky red lines, which don't fit the data at all. And it makes sense because you haven't learned anything from the data set yet. And so if you want to learn the data set, you have to posit some form of inference. And so here what we're going to do is use this technique known as variational inference. And what variational inference does is it just posits an approximating family, and that approximating family is going to try to approximate the posterior distribution. So in other words, the distribution of your weights and biases given your data set. And here we are therefore writing down key W0 with W1, B0, and B1, and they're also going to be normal distributions. There are some details around how you specify these things. I won't go through that now, but just give you an overview of what the syntax looks like. You do that here. Then when you actually do a form of inference, you just pair these things up. So you have W0 and QW0, you have your data, and then you run your inference. Here we just shown that it takes 12 seconds, and after you visualize the posterior distribution, you can see that draws from your posterior distribution actually fit the data set. And so you can see that the generative model actually interpolates well among the data sets within that domain. Does that clarify some things?
It's clear to me. Maybe I'll just make one comment here is that in this plot, well, it looks like a bump, and it looks sort of, but we shouldn't interpret that bump as a distribution. It's really the x is some, independent variable, and the y is sort of some dependent variable. And I know that there are many fields where you have these kinds of, y as a function of x relationships, which you're trying to do some inference about and some kind of regression. And surprisingly, in particle physics, we don't really do that very much. Most of our plots we're looking directly at the densities. So if you want, it would be conditioned on your x, what does the distribution of y look like? And so, which is kind of implicit in these plots. And I think it's fine, but just again, it's more of a message kind of to the physics community that, but I don't know if others want to ask questions here. I've talked to you some, so I
I think visualizing these distributions gets difficult primarily because there are very high dimensional parameters. In this case, it's sort of toy, but even in that, like 6 parameters, and then there's a question of how do you visualize all 6 dimensions. So how we're doing that is we're just going through the generative process, and then we're visualizing what is the underlying distribution of your data with that distribution over your parameters. And so the generative process is simply you draw parameters from your posterior distributions, then you pass it through your neural network, you draw the normal distribution with mean given by the neural network. And because the data set is not that noisy, you can see that most of the draws lie precisely on the same line. And that makes sense, that the variance is low as you fit it. Okay. I can skip through some of this. Maybe here's an example to better relate it to simulator-based models. So here, what we've used is try to do like simulators for population ecology. And as an example, what we're interested in is trying to understand how prey and predator populations grow over time. You can imagine that they're in this anti-symbiotic relationship. And so how does this work? First, we're going to put a log normal distribution, in other words, a distribution from 0 to infinity over 3 different parameters, and we'll write this down to beta. And then we're going to put down these 2 Python lists, which are x1 and x2, representing the prey and predator populations. And now we're going to simulate the prey and predator populations over time. So for each time step, we're going to write down this set of equations. This set of equations comes from the ecological literature, which is just saying how does my x1 depend on x2 and its time step for it, and then there's some normal noise attached to it. You go through these time steps 1,000 times, you plot the simulator, and then this is what it looks like. And given that you've just posited this model that has 2,000 different observed variables, you can then perform inference over the betas. And there are many ways of doing this. You can fit a histogram, then perform some form of maximum likelihood, or you can just look at likelihood-free inference methods. Cool. Let's see. I can go through one more example just in terms of benchmarks. So here, I'm not sure how many of you are familiar with Hamiltonian Monte Carlo. This is sort of one of the main methods for doing markup chain Monte Carlo literature. And so what we're just doing here is we're comparing to previous frameworks, and we're just trying to show how much you can benefit leveraging GPUs and matrix multiplication. So we've just fixed this experiment where we are doing logistic regression, but just putting a prior distribution over the weights, and we're fitting 500,000 data points in this cover type data set. And in the runtime comparisons, you can see that Edward tends to be orders of magnitude faster, and this is primarily because we can leverage more recent hardware. And I guess I can just wrap up very quickly. So Edward is really just this library that's designed for fast experimentation, and hopefully through some of these examples, you could see just the diverse sets of models that you can try to apply. And really, we've also emphasized speed, so it features significant speedups of existing systems, and it tries to really bridge this this notion of research design and deployment, such that you sort of get the best of both worlds. And if you're interested in more, you can go through the website, and we have tons of documentation and contributions as well. So thanks. I think I can just stop there, and if you're interested in more, please email me as well.
Great. Thank you, Dustin. So I think there's this idea about being able to leverage the GPUs is definitely something that, within this Diana forum, there's a fair amount of effort for trying to take advantage of GPUs, but with the types of statistical procedures that we've usually done, things that are closer to maximum likelihood estimates, where you're providing some, type of, likelihood function which was created through, traditional means by physicists. One thing that's a little bit interesting is that in our main statistical package, we don't have autodiff. So the way that the actual minimization happens is we use a tool called Minui, which has something sort of like LBGF as like minimizers and things like that, and it's very much based on finite differences and things, and it can be slow and unstable. So there's been some look into trying to include auto-diff into the framework, but since it didn't really have that at the beginning, it's a bit difficult to kind of add that after the fact. So I think that's one of the places where certainly several of us have been looking both into how we get auto-diff into the picture, and secondly, different kind of underlying tools for doing GPUs and things like that. So I think if we wanted to try to kind of merge these efforts a little bit, I think part of what the community would be quite interested in is the modeling side of it. And so maybe you can say a little bit about if we started using Edward and we wanted to start including, because we have lots of distributions that are not, that are inspired by physics and not going to be inside of Edward. So maybe you can walk us through a little bit the process by which a user would add additional, random variables / distributions, and maybe a little bit, maybe even in terms of some mechanics of, are those in separate packages that are linked together, or are they in the TensorFlow side, or would they have to be a contribution to Edward, the big package, etc.?
Yeah, so that's a great question. So you can definitely so I think there are two things. One is if you're going to develop new random variables. So what I think of as a random variable is like a core primitive. Like it has a log probability distribution or as a sampling generative process. And so there's documentation through the website. And once they're implemented, we can go through. I can go and help, and we can submit this to be directly in Edward itself. There seems to be there's also another issue, which is just about building simulators and performing inference on these things. I think maybe an easy way to help bridge this gap is to write down these models first, and then we can use the current inference methods, but just have them deployed in Edward. In other words, like you fit a histogram, so you have some proxy to the likelihood, and then you can run standard likelihood-based methods, or you can just try other fundamentals, such as like you draw data from the model, then you perform a form of rejection sampling or any of this stuff. I was focusing a lot on the state-of-the-art methods, but really I think you can get a lot of benefit just from the fundamentals, whether it be like auto-diff or this generative process with the modeling language.
Right. No, I agree. But can you say a little bit more about, I think the workflow of our groups a lot of times is that people will develop packages with the set of distributions or random variables that they need for their particular paper, and they're not general purpose enough that, well, there are some people probably wouldn't want to put it into like the general code base for several reasons. So is it designed in a way that is any kind of impediment, or is it very easy for me to like create some kind of my Edward random variable package and then just somehow link it and then use the rest of Edward's inference?
Yeah, they're implemented just as classes, and it's easy to write a subclass that inherits from like a base random variable class. And then you could just use it in your own code base, and I think everything should be fine.
Okay, that's great. Yeah, so we have one of our Diana fellows is working a little bit in this direction to try. So I see Matthew Feikerth is connected actually. So he's working on trying to do this kind of histogram-based approach, but also a lot of times we don't have just one histogram. We run the simulator with different sort of settings associated with nuisance parameters, and then we have a collection of histograms, and then we have to in some way interpolate between them to make a continuous likelihood model, and then that's what we end up feeding to the inference algorithm. So I think it's likely we'll come back to you for maybe some help about that process, but that's the kind of direction that this is going.
Yeah.
I'm hogging a lot just because I'm trying to help. Since I know that there's a pretty big language barrier, I'm trying to help, but I hope other people have some questions or comments or something along here.
So sorry that I came in late, so that's why I was reading up on the webpage. Trying to see how does this add value over doing the modeling directly in TensorFlow, where you do get things like automated derivatives and things like that. What is it that I'm missing that the features?
Yeah, that's a great question. So the TensorFlow, so Edward is really you can think of it as not one abstraction layer on top of Edward, not on top of TensorFlow, but on the same level as TensorFlow itself. Because what it endows you with is a notion of random variables, like a notion of randomness, and that's something that TensorFlow doesn't have by itself. So you wouldn't be able to write down a model and then perform inference in TensorFlow. You can think of TensorFlow just as a bunch of tools that allow you to do matrix multiplication in similar or matrix multiplication and draw some randomness in the same way as like eigen or like other primitive sort of numerical computing libraries.
Yeah. Can I mean, the way that I was thinking of it, so maybe you can correct me or comment about the way that I was thinking of it, is, and again, I'll kind of tie it to our physics side. So on the physics side, we have a tool called, like a framework called Root, which provides a lot of math libraries and ability to read data and has some minimizers and things like that. And then, but it doesn't have a really, initially it didn't have any kind of statistical modeling language. And then we developed a package called RooFit, which sits on top of that. And I wouldn't call it really sits next to, I would think of it more sits on top of. It is true that it's adding that's where you get the notions of random variables and things like that and distributions and blah, blah, blah. But it's built on top of those math libraries, and then it also uses the minimizers and things that we have in that package. And then what was missing, that was used for a long time for doing statistical analysis, but it didn't actually provide the inference algorithms themselves. So people would have to write the inference algorithms on top of that. And then we added another package called RooStats, which sits on top of that, which is essentially the statistical, the set of statistical inference tools that use the RooFit modeling language that use the, Root math libraries and I/O. And that's kind of how I think of it. And that Edward is providing both the library for inference, and it's also providing the modeling language, and then it's sitting on top of TensorFlow, obviously extending the primitives that were in TensorFlow. But
that helps a lot.
I think
Well, another thing that I was thinking about was when you were talking about defining new random number distributions. Is there's a way you were talking about rejection sampling, which is not very efficient, and it can be very bad depending on the distribution. A fairly good way of representing random distributions is with a function that is the inverse CDF. This is the way that mathematicians represent random numbers. So that delta masses within it become discontinuities and such like that. Can you provide new distributions that way? Because that would be a very powerful way to add distributions. In particular, if you have a histogram, then you can add that function via histogram lookup.
Yeah, question. So I think that's possible. The way I think of it is that you're just writing a function that will give you some output. It can also just be a deterministic output. Most of the random primitives that are put inside Edward or TensorFlow more broadly are through deterministic functions. The normal distribution, for example, is written by drawing from a uniform and applying appropriate transformations on it. For slightly more complex distributions, like with gamma distributions, you have to do a form of rejection sampling, but for the majority of distributions, we have efficient samplers, and there's a ton of support for you to also build sort of like whatever functions you like over uniform noise.
Right. This is generalizing that. The appropriate transformations you refer to is this function.
Yeah, but that's a very I mean, well, Dustin's a statistician. He knows these but I mean, to be able to do that transformation means that you need to have the inverse of the CDF, and that's a very kind of special set of cases that how to do that. I mean, in principle it's there always, but it's in practice it's very infrequent. You know how to do. Can I ask a question? If you have a complicated kind of black box generative model, and you wanted to wrap it into this distribution class, but the implementation of that is not in TensorFlow because it's some incredibly complicated simulator the field has already created. What thing in terms of, so for instance, you won't be able to pass derivatives through this thing and et cetera. What kinds of, can Edward handle that? Can you satisfy this interface if it's just some, that given some parameters it can generate some data, but it's totally black box, non-differentiable?
Yeah, there's a function called something pyfunc, and what that allows you to do is wrap any Python output. And this is a way of so TensorFlow has this computational graph, and basically what this does is it represents all your computation, and you have to write anything as part of this graph. And so what the pyfunc allows you to do is it wraps any of that Python output into the computational graph. And if you have a black box model that only has like some output or some given some, it will produce an output. It can be random or deterministic. The pyfunc will allow you to represent that in the computation. You can also register gradients for it. And so if you know the gradients of that black box function or simulator beforehand, you can leverage that, and everything will in principle distribute well in the environment.
Great, thank you. And so I have a couple other questions. So in the language that we use now, a lot of times when you implement a new distribution or random variable, sometimes you have an explicit formula for sort of what the density looks like, but you're lacking the normalization constant. And the framework will basically, the interface for that set of classes and our framework is, there's abstract functions and abstract PDFs, and the PDFs have to be normalized. And but when you implement them, you just provide something proportional to the PDF, and it will sort of and there's a hook to provide an analytic normalizing constant if you know it, but if you don't, it will resort to some one of various approaches to try to do it. So one question is how you deal with that, and then there's another question I had about caching, because those kinds of constants are very expensive. So usually you want to try to cache those numbers, and you can use it until you change some parameter of the distribution, which makes that normalizing constant irrelevant, and then you have to recompute a normalizing constant again. So so can you say a little bit about the normalizing stuff, and also if there's any attempt for caching, or if you've not found it necessary?
Yeah, the log prob. So there's a method in all the random variables, which is just the log probability density function, and I don't think that any of them have to be normalized, although it depends on the inference that you're performing. I'm not sure if we have documentation on that, but I think it's definitely possible to just represent the unnormalized version and perhaps provide an additional method to include the normalizer. For caching, I'm not sure if there's an explicit way to handle the caching. The majority of it is tried to be done automatically for you within the graph and as you run the session. But I think there are methods, there are functions available in TensorFlow. This is not something we've done, but in TensorFlow itself, that allows you to more finely control that memory access.
Okay.
I'm not sure if that answers.
No, I think it does. I think there's a little bit. I mean, certainly when you go from the PDF to the log PDF, this normalizing constant is just kind of an irrelevant constant. But if that constant changes as a function of the parameters, then it's not irrelevant, right?
Yeah.
So that's the kind of situation that I'm mainly worried about. So a lot of times the dependence of that normalizing constant on the parameters, people don't know what it is, and that's what the system is essentially computing for you.
I see. Yeah, I guess in my terminology, I wouldn't even think of that as a constant once it depends on the parameters. But I guess if it is something that you wouldn't want to include into the log probability distribution, you can just write it irregardless of like an additional thing that should be inside, and then maybe afterwards you can include into another inference. But maybe it would be helpful just go like we can go through a particular example and see how that might work out.
Sim, maybe you could say a little bit to this community about both like TensorBoard and also what you do in terms of graphics. So in our current, if I compare this to RoofIt, one of the things that good or bad about it is that it's in a dependency way it's bad is that it's tied up to a bunch of plotting and graphics and visualization tools. So dependency-wise, that's a kind of a pain, but of course you can get some pretty powerful visualization out of it. So so I think if we try to move our community in this kind of direction, then we need to build up that equivalent plotting and visualization layer. Can you say a little bit about how you think about that?
Yeah, I think of that in two parts. One is visualization internally in terms of like the computation and diagnostics that go inside the algorithm. Those are things that we natively support, and those things are through what Kyle's mentioning is TensorBoard. And TensorBoard is just this web interface that allows you to visualize all the computation that goes inside the algorithm and a bunch of diagnostics, for example, like loss functions, over time, wall clock comparisons, parameter fits as they change. For more exploratory output, all that we rely based simply on Python itself. The output usually of your algorithms is just a bunch of NumPy arrays, and you can sort of manipulate them as you like.
Yeah. Do you feel any pressure from your users to start to make a package just using that, but it's starting to it's a little bit tailored for the types of visualizations you would want to do in a statistical inference side? Yeah.
For the summaries that we've been basically writing into TensorBoard for the internal diagram, most of those have just been generic, and I think we've tried to stick with the design of keeping them generic such that it will try to benefit as many people as possible. For the exploratory output, we haven't built too much infrastructure for that, except for things like checking your model fit. For the majority of those, I think we've eventually settled upon just making them be example specific, and there has been some collaboration that we've been doing with like PyMC3 and Stan to get like exploratory output that might be useful for visualizing output from Stan or any of these other languages. We haven't totally settled upon it just yet.
Okay, that's interesting.
Could I make a suggestion along those lines? If you're dumping the relevant data into NumPy arrays, and you just want to make it easy for people to explore that, if you have a simple wrapper to turn those NumPy arrays into pandas data frame, just like 2 lines or so, a method just for convenience, then they can do whatever they want to do to plot. You've just given them all the plotting routines, the basics, just inherited from pandas.
I didn't hear you, Jim. If you could turn them into what?
Oh, pandas data frame.
Oh, yeah, okay, sure.
So that you, in this project, in Edward, you don't think about how are they going to make histograms or scatter plots or whatever. You just give that problem to pandas.
Yeah, that's a great suggestion. I think that's what we're trying to do. We'd like not to put visualization infrastructure into Edward, because I think once you start adding too many things to the library, it just becomes unwieldy and
yeah. I wouldn't want to put it there either. I wouldn't want to put it there either. But I am imagining that as a kind of potentially necessary side project is that visualization layer, because there are a lot of standard kinds of plots that you want in a particular inference setting, and making those from scratch all the time is kind of painful. yeah, I wouldn't want to put it in Edward, but like Edward plots or whatever. I don't know.
So the reason that I'm suggesting that is because then you could have user examples that are things like Edward something, Edward something, Edward something, dot 2df dot xplot or scatterplot or histogram, or so the in between is just a dot 2df or dot df or something, and have that method import pandas within the method. Right, so you're not actually depending on it. And then you can have all these examples that look short and sweet, and it's easy for people to explore. But you've not actually had to go through defining what plots people are looking at as part of the library. It's just a suggestion of offloading that.
I think that's reasonable. Maybe that's the right way to go forward. The current way we're doing it is that each script has its own plotlib function, whether it be like going from NumPy array to pandas data frame and then making a scatter plot or a histogram. But maybe it's better to just have some minimalist collection of these functions and stamp a package name to it. But I think either would work.
I have another question. Sorry, maybe I missed because I came a little later. But did you mention how Edward is compared to other probabilistic programming languages like PyMC and Stan and BiasLoop maybe?
Great question. I think the main distinction is that Edward is trying to be less automatic, and what I mean by that is that you should have a toolbox for you that allows you to very quickly experiment with both the modeling and the many variety of tools that you're doing to do with the fitting of the model. And for things like Stan and PyMC3, and the majority of probabilistic programming since like 2014, I guess, all of those have really emphasized this automation where you just write down your modeling spec, and then there's some black box function that will give you output. I think for rich sorts of experimentation, you need slightly more fine-grained structure, and that's what we've really been trying to emphasize a lot in Edward.
Okay, thank you.
Great. Well, thank you again, Dustin. I don't know if others have questions, but I think it's definitely it's very interesting. I look forward to working with you some more on this, and we'll see what happens a little bit with this project that we have as our first kind of attempt to do some simple versions of our problems in this framework.
Cool. Well, thanks everyone for coming as well.
Does anyone else have any questions, or not? We're right about an hour, so. Okay, well, great. Well, thank you again, Dustin, and I hope to see you again soon. All right.
Thanks.
All right.
Bye-bye.
Thanks. Bye-bye.